All right, Calc 3, welcome in. It's Tuesday, September 14th. It's the start of week 5. And today we're going to be finishing chapter 11 by covering 11.7. We're going to learn cylindrical and spherical coordinates. Since we're finishing chapter 11 this week, that means the first exam covering chapter 11 will be open next week, right? And so I envision that opening up on Monday night. A week from today, a week and minus 1 day, so the 20th, right? That means that chapter 11 test will open up on the 20th, and you'll have until the 26th to take care of the 2 parts of the exam, right? There's going to be a online part that you take, very similar to your quizzes, right? So about half the points or so are coming from those sorts of questions that can easily be done, graded by a computer. And then there will be a written part that you have to submit and take a picture of, maybe scan it in, however you get that done, as a PDF or whatever, and load it up into the assignment like you did for the survey in the beginning of this semester, yeah? So that will be open next week. So you want to definitely be preparing for that, because there is a time limit for the online part, but it's a generous time limit, because it's like half an exam, but with the full period of time that you would normally have if this was in person. And then the written one, of course, you can work on it all throughout the week and then submit when you are happy with it, right? As long as it's before the deadline. So let's see. If there's any questions about anything like that, go ahead and in chat, you can talk to me about that. And so if there's any questions about the exam, what it might be like or whatever, let me know. If you have questions on YouTube, email me those questions if you have any on that. Yeah, what do you got?
So like in terms of material, you'd obviously recommend just going over past quizzes and some of the homework,
Yep,
concepts.
exactly. Yep, exactly. I would recommend, let me see if I got it up here. Oops, no, that's stats. That was my last class. You don't care about stats. Hold on.
Because like the homework, like in the list, it shows all the concepts like
Yep.
that we were supposed to do because that's how much you covered in that section.
Yes,
But it's just
exactly.
like not
It's
saying that it's not like worth the
it's a
time. I don't
lot.
know if I have time to do 99 problems to go
Yeah, yeah,
over
yeah.
them.
Yeah, so you sort of want to, be efficient, right? And on what you work with, right?
Yeah.
So I tend to, I'll just tell you, at the end of chapter 11 here, see there's review exercises. Yeah. See calcchat.com for tutorial help and worked out solutions. And so this is a great place where I find questions, and they're sort of all located here. So in preparation for this, I would look through these problems, and one, they're new problems that you probably haven't done yet. Two, just look through the things that we've done, right? Like being able to write vectors in different forms. We did problems like that. So maybe look at that, right? Finding a vector. We did something like that. Find the distance between 2 points. And so you can go in through here and say, yep, we did a problem like that. We did a problem like that. And you'll want to maybe practice here. It's all sort of condensed, right? And even in order of the chapter. So I highly recommend studying in that way. All right, so you're doing stuff, you're calculating things, you're practicing the calculations that we had, and there might be things that we didn't cover that you can skip, right? I'm not seeing anything. Oh, symmetric equations. We did not do symmetric equations, so you can do skip that. Finding an equation of a plane, we totally did that. Finding the distance between a point and a plane, point and a plane. So there's more than one of those types, right? So maybe do both if you're uncomfortable. But if you're comfortable, maybe do, just one. And then there's some other smaller problems, like surfaces of revolution we did not do. So you could skip those. So that's what I suggest. And sketching a surface in space, you won't have to sketch. It'll be a matching, just like the homework one was in
Yeah. Like the
11.6.
straight line.
Yep. So that's how I would approach this.
And this is at the end of the chapter, correct?
It's at the end of the chapter. Let me show you. It's a page. What page is this? It's covered up on my screen. 815. 815. So this is at the end of chapter 11, review exercises. Now, I am apt to ask some true-false questions sometimes. True-false questions are contained usually in the homeworks. It doesn't look like 11.7 had any, but let me see about 11.6. Let me look back here real quick. Some of the recommended problems, it said, hey, if it's, sorry, I'm scrolling a lot. Divert your eyes if it's weird. Let's see. True or false. See this? So like in 11.5, there's a little bit of true or false questions, right? So I don't usually stay up at night inventing new true false questions. So I usually grab them from the book. So you might want to look at true false questions. Those are easy to ask as multiple choice questions, right? Because it's either true or it's false, right? So those can form a bit of your things as well, right? So talking about concept, and I always try to put true or false questions that have talked about concepts that we've talked about. And so that's how I would study. Doing things by doing the review exercises, practicing those basic calculations that we've been doing, and then look at the true false. Will there be a section we have to upload or anything like that? Yep, that's the second part. That's one where you have to show your work and take a picture of it, run it through either Cam Scanner, that's really nice program to do PDF, or make it real nice to upload. Yep, so there will be an online part and an online submission part. So, yep. So there'll be both.
May I ask,
You may.
how many questions will there be for the exam?
And the answer to that is I don't know. Yeah,
Okay.
I don't know.
Could I expect maybe 3 or 5 questions per section or something?
I don't know if I would put it that way either. I'll say that everything will be represented that we've done, right? And so I don't know if I can say it specifically as there's going to be 3 to 5 questions from each section, but I do try to make sure that every big idea was covered.
Sure.
Right.
Okay.
So I don't know if I can give you any better answer than that without stretching the truth a little bit of what might happen. Because one, I haven't put it together yet, and two, if I said there was one question on the exam, would that make you feel good? Probably not. If I said there was 20, no, I don't know. Right? What's the right answer to that question? I don't know. But the expectation is I'm going to ask you the similar questions to what we've done on quizzes, similar concepts, similar calculations. Right.
Understandable.
Yeah. So that's kind of my philosophy on making that, right? Okay. All right. Are there any other questions about, well,
One last
exam?
question.
Yeah,
I
go
don't know
ahead,
if I just
please.
didn't hear you or if I, spacing out, but how much time do we have on the exam? You said we had
Ooh,
like what
that's
time?
I was afraid you were going to ask that. I think, don't quote me on this, but I think it's 75 minutes to do what I would consider half of an exam.
Yeah. Okay.
So that would, well, actually, it's actually more because Calc 3, see, I'm basing it off of the in person. So Calc 3 in person, you would have met for for 100 minutes, for 100 minutes. So I think my time limit is 100 minutes, but it would be just for half an exam, if that makes sense.
Yeah.
So my in class would have 100 minutes to do the full test, right? So there's a little bit of give there a little bit. So I'll tell you this: no student has complained about the time limit ever.
Okay.
They felt there's plenty of time, and I've not seen anybody actually utilize the entire time or needed the entire time. I've not had anybody complain about the time limit. It's just there so there's some sort of cutting off point for the online thing, just like the quizzes, right? The quizzes have a time limit. But of course, the written stuff you work on throughout the week and then submit when you're ready. So the only time limit on that is submitting before the deadline. Please don't wait till the last minute. You know that's when your computer's going to crap out. That you know that's when the internet's going to go down, right? So don't say, well, I'll upload at 11:59 or 11:58 p.m. on Sunday. Please don't do that. Don't risk it, right? So anyway, and that's a general you. That's not a specific you to anybody, but just these are things from students past that have that have played a little around with the deadline. You know that's when your computer is going to screw up. So, or Eagle, right? I mean, it could be on their end as well. So, all right, I think that's good. If you're good, I'm good. I'm ready to move on to 11.7, unless there's any more questions. All right, sounds good. Let's get on with some content. So, what we're working on today is a couple of different coordinate systems. Now, a coordinate system is a way that I can address certain points, right? Like, where does this point in space live? And of course, we're very much used to what we call a rectangular coordinate system, right? So we're going to look at a couple alternative coordinate systems that really have their place, and when they work, they work really well, and they can do amazing things here. Oh, I just got an unstable internet message, so sorry for Zoomers here that you might have seen me sound like a robot for a little bit. Hopefully it's back. But we're talking about cylindrical and spherical coordinates. Two different coordinate systems, right? Okay. Like I was saying, if one of these special coordinate systems work, man, it can really simplify our work, our life, what we have to calculate. Of course, they're not applicable in all situations, and it can be worse, right, in those sorts of cases. But when the situation calls for it, they're really nice coordinate systems. All right, let's go ahead and let's start with cylindrical. How does that work? Okay, cylindrical is going to have three coordinates, and we call them r, theta, and z. Okay, r, theta, and z. Okay, r and theta are exactly the r and theta of polar coordinates. And so we say that r and theta is a polar representation of the projection of the point. I'm definitely going to draw a picture soon, right? But I want to put down a definition first. Right? Projection of P, the point in the XY plane. And then Z is the directed distance from that projection, r comma theta, to the point P. Hopefully this will make a lot more sense once we get a picture drawn. All right, but that's in words what we got going on. So here we go. Draw a quick 3D picture here. Here's our x-axis, y-axis, z-axis. And just to put an interesting picture over here, I'm going to put the dot right here. So this is point P. And I'm actually going to draw it in such a way that its projection is over here. Okay. So everyone with me, see that, how that's over here? It's behind the YZ plane, right? It lives over there. Yeah. Now a couple helper lines here. What I'm going to do is need to draw along the XY plane, draw that distance from the origin, or in polar we call it the pole. And we go to the projection of this point. Now the projection is the shadow that this point casts on the XY plane, right? And so we call that distance r. We call this distance here, z, is the directed distance from r theta to P. So this is z, the height. And theta is measured from the positive x-axis, just like it is in trig and polar coordinates, right? So here we go. Here's how I can work with this coordinate system. I can tell you where this point lives by telling you what angle to swing around horizontally, right? Then go out a certain distance r that is either negative or positive. In this case, it's positive. You go till you're underneath or above the point that you're at, and then z makes you go up or down to reach that point. In this picture, it looks like z is positive. You see that? And so that will allow me to tell you where any point in 3 space lives. I can give it coordinates. I can give it an address. Where does it live, right? And what's nice about this is that it gives us connections because it's so much related to polar, right? In fact, I call this sort of a hybrid coordinate system. That's my own word. I've not seen that anywhere. But this is a hybrid coordinate system of type. In other words, one part polar, the other part rectangular, right? So it's sort of like a hybrid model of the two sorts of, here's an angle type measurement, and here's a rectangular type measurement, right? And it's a hybrid of the two. So cylindrical is a combination of that polar and one rectangular, right? Okay, so now let's see if we can remember or recall at least our formulas for the conversions and such, right? So now let me draw a couple more helper lines here. This along the line here is going to be a distance of y, right? That's going to be the y coordinate right there. And this distance here is the x, right? From there. Okay. And so what I would like to do now is sort of get a description for x using r and theta and z. But since this is polar, we can just recall the formula from polar coordinates, which you might recall is x equals r cosine theta and y equals r sine theta. Since I'm borrowing the r and the theta from polar, I end up getting the same formulas there. So this will be from cylindrical to rectangular. Right, so if I want to convert between the two, right, the x coordinate works this way, the y coordinate works this way, and what is maybe the most difficult, wink wink, conversion formula of them all, the z in rectangular is equal to the z in cylindrical. Yeah, because it's the same thing. And so just for completeness, what's the x coordinate? That. What's the y coordinate? That. What's the z coordinate? Well, z, because z is allowed as one of the descriptions here, right? So there is no conversion, right? Because it's already itself, yeah? So these are going to be very helpful to memorize and to know. Those are connections between, if I give you a cylindrical coordinate, you should be able to now come up with a rectangular coordinate, its x, y, z coordinate, on where that point lives. Right? Now we can go the other way as well. So if I give you a rectangular coordinate, can you convert it to cylindrical? Yes, and there's ways to do that, except it's a little bit indirect this way. Using Pythagorean theorem, you might recognize that this is a right triangle here. And so this is the hypotenuse, r is the hypotenuse. So we certainly have this relationship, r squared equals x squared plus y squared. Right? And that's coming exactly from this right triangle that's living in the floor of the xy plane. Yeah? And so we don't, we don't write this as r, we write this as r squared. This tells you something very interesting, that r has two ways to look at it. R could be positive or it could be negative. And there's going to be a different aspect for those both. And we'll see that as we start working with the problem soon. So remember that r can actually be positive or negative, but squaring it, of course, will always be positive because this will always be positive. Yeah. Now, a formula for theta that we often use, it will be the tangent of theta. Again, this is borrowed from polar, is the y coordinate divided by x. I mean, that's straight out of trigonometry, isn't it? That's the y coordinate on a circle divided by the x coordinate of a circle is the tangent of the angle that it makes with the positive x-axis. And so that formula allows us to get theta. Now, with any trig equation, there's some trickiness here, because if you know that tangent of theta, if this is a positive number, remember there's two options where theta can live. If tangent is positive, theta could be a first quadrant angle, or it could be a third quadrant angle, because tangent is positive in the third quadrant. So just knowing whether this is positive or negative, there's actually still some ambiguity in what theta is, where theta exactly lives. So going this direction, rectangular to cylindrical, you're going to have to actually do a little bit of detail checking to make sure that you're not accidentally picking the wrong quadrant. You could have quadrant issues when you go this way. This way, it's easy. You just plug in and you can't go wrong. X, Y, Z is a formula. You just plug it in and calculate. No ambiguity at all. This way, there's options. And you have to make sure that you're not picking a combination of options that are incorrect. Yeah? But thankfully, Z of cylindrical equals z of rectangular. And so we have our conversion formulas. All right, so those are our conversion formulas for that. Let's now utilize these in our first example. Okay, so let's try this. Let's convert. This is a cylindrical point, and it's given to me as 4, comma, 5 pi over 6, comma 3. Okay, so that's a cylindrical coordinate, and I want to convert that to a rectangular coordinate. Okay, so I want to convert cylindrical to rectangular. So if I'm given that this is cylindrical, respecting the order in which we're told these things are listed, this I know is r, this is theta, and this is z. Right? So we do know that r is 4, theta is 5 pi over 6 radians, and z is 3. Okay. Now knowing that, it's as simple as just plug and chug, right? We just can say, okay, great. If I know r, theta, and z are these, here's what I know. X has to equal 4 cosine of 5 pi over 6. Y has to equal r sine theta, so 4 sine 5 pi over 6. And then z has to equal, well, z, so 3. Yeah. And so there I have it. Now I just have to actually just calculate this. Cosine of 5 pi over 6. Now 5 pi over 6 is a second quadrant angle, right? It's over here, like that. And so I know cosine is negative over there, and sine is positive. And now I just have to remember what value that is. And so this is the long x value. So this is going to be negative root 3 over 2. This is going to be 4 times positive 1/2. And then this is still 3. And so I get that this is negative 2 root 3. This is 2. And this is 3. So my coordinate in rectangular space is negative 2 root 3, comma 2, comma 3. And so that's the coordinates of this cylindrical point. Now, please draw a picture, right? Draw a picture to help you, especially not necessarily with this direction, because this direction, the formula is just, you can plug it in and you're good. But please try to visualize where you're at. And this is going to be more important when we go the other direction, right? So I really want you to draw a picture here. And this is good just to picture where this lives, right? So let's see if we can do that real quick. All right, just a quick sketch, at least to know where this point lives. All right, so the r is 4. That means whatever angle I'm looking at, I am going to take 4 steps forward. Okay, so I don't tend to look at r first. I tend to look at the angle first. So picture yourself at the origin, picture yourself at the pole here, rotate 5 pi over 6. Right, so I'm going to rotate. Here is pi over 2, that's 90 degrees. Pi over 6 puts me in the second quadrant, right, sort of like along here. It's the top view of this picture, right? And so there's the angle of 5 pi over 6, just like that. Now, along that, move 4 units. 1, 2, 3, 4. This is the projection of the point in space. Yeah. Now from this point on the floor, go up 3 units. So 1, 2, 3. So my point is roughly right there. Agree with that? Would you agree with that? Yeah. That's how you would think about visualization, right? This helps you because notice that this point is above the second quadrant. So you're in the second quadrant, and that's good to know, especially when we go look at the other direction, right? Now check the answer that you got here. I got a negative x value. That makes sense because negative x value would make me walk backwards a certain amount, then go positive y value. So that's positive 2. That would end me up here, and then go up 3 to the point where I'm at there. See that? So this answer makes a lot of sense, right? Just physically and geometrically, that makes a lot of sense. And of course, because the formula said it was supposed to be that. Okay, how are we doing with that? Any questions on that, the visualization or anything like that? Okay. All right, let's go the other way. Let's see here. Let's do this. So now let's say that we have rectangular points, coordinates, at -1, comma, √3, comma, 2. And I want to convert that to cylindrical. Okay. So now in this direction, man, I really want you to draw a picture so you know exactly where this is, because now I have to start making some decisions on whether I want r to be positive or negative, and what angle theta, which quadrant that lives in. So I have to start making decisions and be consistent once I've picked my decision. There's going to be two options, though. In fact, there's lots of options for cylindrical. In fact, if you think about it, since it's polar, remember polar gets you to the same place when theta is any 2 pi multiple, right? You can just keep adding 2 pi and it brings you right back to that place, right? This brings up the fact that cylindrical coordinates are not unique. In other words, there's more than one address that I can give to the same point in space. Now, some consider that a weakness of cylindrical coordinates, right? Why should this point in space have more than one address, right? But it's so helpful in simplifying things that rotate around an axis, right? In other words, a cylinder, if you will, right? It's so helpful for those sorts of situations that we'll take the hit that it's not unique and just deal with that. And that's going to be better to deal with that than having to deal with the rectangular awfulness of trying to determine, curving things in a rectangular world, right? It's kind of difficult to measure curves and circles and cylinders and curves that curve a lot with straight lines, with rectangular coordinates, right? That sometimes doesn't go as nicely as you would hope, right? And so it's nice to have other options. Okay, so I want to convert this rectangular point to cylindrical. First, let's get a fix on where this is at. Okay, so the x-coordinate, right, is -1. This is y, this is z. So the x-coordinate is -1. So, oh, yeah, see this? It's in the second quadrant over here. So there's x being -1. Y is square root of 3, so that's a little bit more than 2. So I'm going to go 1, 2, and just a little bit past that. So I'm going to say that the projection lives there. And then 2 up. So 1, 2. So let's say it lives about there. Okay. All right, would you agree with that? That's roughly where it lives, right? -1, square root of 3, right? 2. And in fact, I could draw that, 2 square root of 3 there, do 1 there, -1 if you wish, right? Something like that, okay? Now, let's see what we can say. We know that r squared is equal to x squared plus y squared. That tells me that r squared is going to be -1 squared plus √3 squared, which is going to be 1 plus 3, which is 4. And so r looks like it has two options. R squared being 4 means r can be plus or minus 2. And here's where I have to make my first choice. If I choose r to be positive 2, then that means I want to walk forward from the origin. You see that? So if I have to hit this projection spot right there, I better be aimed this theta. So if I pick r to be positive 2, theta better live in the second quadrant. On the other hand, if I pick r to be negative, r being negative means I walk backwards from where I'm looking, right? So if I'm looking this way and r is negative, that means I'm actually going over this way. I'm going the opposite direction. I'm taking a step backwards, right? I'm looking this way and walking backwards, right? That's what an r being negative would mean. So if I wanted to pick r to be negative for whatever reason, do you notice that I would have to actually spin all the way around to be in the fourth quadrant over here, look this way, and then walk backwards 2 units. But do you see in that case, theta would be in the fourth quadrant. So if I pick r to be positive in this case, theta needs to be in the second quadrant. If I pick r to be negative, theta needs to be in the fourth quadrant. So let's go ahead and deal with that now. I'll pick r equaling positive 2. So theta is second quadrant. Okay? And I'll go back and do the other choice and show you what that answer would look like at the end of this. So I'm picking r equals 2. So theta is second quadrant. All right? Now let's get a hold of what theta is. Let's bring in our other formula. We know that tangent of theta is equal to y divided by x. All right? Which tells me in this case that tangent of theta equals y is root 3, x is negative 1. So this is going to be negative root 3. Now that is a special angle, right? If I was to figure out the theta of that, that ends up getting me pi over 3, right? If you take the arc tangent, for instance, using your calculator, right? So even if you put your calculator in degree mode for a hot second here, right? And I did, okay, what's the inverse tangent, arctan, of negative square root of 3? See what it tells me there? Negative 60. Okay? That is negative 60 degrees, which in radians is pi over 3, but it's negative. Do you see that my calculator is giving me a fourth quadrant angle, not the second quadrant angle? Do you see that? That is something you have to look out for. So here's how I can handle this. The calculator says inverse tangent of negative root 3 equals negative 60 degrees, or negative pi over 3, right? That's what the calculator told me. But if I pick theta to be negative pi over 3, that is an incorrect answer, right? And why is that? Because if I pick this angle, right, and I rotate now negative pi over 3, that rotates this way. So I'm looking this way. I'm looking this way towards the fourth quadrant. And now my r being picked positive tells me to walk forward 2 units. And you see I'm completely walking away from where my point is. So if you pick r to be 2, and then in this case pick what the calculator told you, you're actually incorrect. Do you see that? You're literally going the wrong way. That's what you have to be careful with, and that's why you draw a picture, so you don't make that mistake. Does that make sense? So now how do I fix this? How do I work this? Well, the calculator did tell me that this is at least a reference angle. I can think of the 60 degrees as a reference angle, so pi over 3 is a reference angle, which means that if I wanted to move the second quadrant angle here, right, like this, since tangent is negative, I will now need to do something like 90 degrees plus that pi over 3, right? Or something like that. Hold on. Oh, yeah, I'm looking at the, sorry. I was looking at my, the textbook, but I forgot I had changed the textbook problem. So then I was like, why did they get that? That's weird. Anyway, back up. What is the angle in the second quadrant? My reference angle is pi over 3. To find the angle in the second quadrant, you measure from the x-axis. So this is going to be pi minus pi over 3 to get me an angle of 2 pi over 3. That's the theta I need. Theta is 2 pi over 3. Not the fourth quadrant version, right? I want the second quadrant version of the angle because I picked r to be positive 2. Do you see that? So this way is tricky, but it doesn't seem like it's tricky. It seems like, oh, I just plug into some formulas. But the trig can get you a little tricky because there's this quadrant issue. There's this quadrant ambiguity, right? So let me recap everything that we've done here. My final answer here is this in cylindrical can be 2, comma 2 pi over 3, comma whatever the z is. The z is 2. That is one possible correct answer. Okay. Another possible answer is if I had chosen, so alt answer, which is totally cool as well, I could pick r to be negative. In that case, I need the fourth quadrant angle. So in this case, I can just pick the angle that the calculator gave me. And then the z is the z. So this is also a correct answer. Either one of those are correct. But what I see students do most often is they'll pick r to be positive and then just put down whatever the calculator tells them. So if you wrote down 2, negative pi over 3, that combination is incorrect. Do you see that? So once you've picked your r, you have forced what quadrant theta is in, and you need to make sure you're picking the correct quadrant. Any questions on that? Are we doing okay with that? That's the trickiest part of this, is just knowing where this thing lives at, right? Now, what are some possible other answers? Well, theta, I could literally add any multiple of 2 pi to this, and it'll spin me right around to the same place again, over and over again. So, you know, anything of the form 2 pi over 3 plus 2 pi k is totally legit, right? That's for whatever k, for k in integer, right? Anything you put in for here is a correct answer for an integer there. Same with this. So there's literally an infinite number of possibilities that are correct, but of course there are many more, infinitely many answers that are incorrect. Yeah. So anyway, that's what we got there. Any questions with those conversions? Any questions with those? Okay. Now, where cylindrical coordinates really shine, okay, is when I'm representing, well, cylinders. And many of the quadric surfaces that we were working with last time have are cylinders, right? Many of them. So let's take a look at something here. So for example, suppose I said, hey, I'm working with this surface, x squared plus y squared equals 9. And I gave that to you as a rectangular equation because it has x, y's, and z's in it, right? And we know this is a cylinder because a circular cylinder, actually, right? Because x squared plus y squared equals 9 is a circle. There's no z value, and so the z can be any height it wants to be. So I just get this circle at any height. And so this is a right circular cylinder, infinitely tall. Okay. I want to convert this equation to cylindrical, okay, to CYL, cylindrical, right? So what that means is x's and y's are not allowed, only r's and thetas and z are allowed, right? So I have to make some change to the x's and y's, but I have to keep the equality true, right? Now, luckily here, we have a very cool fact about r squared, right? Remember our formula, r squared equals x squared plus y squared. So this one's simple. All I have to do is replace this with what it's equal to, which is r squared equals 9, right? And so you can leave it like that, or you can go further and say that r is the square root of 9, which is 3, right? That's an option. Here's another correct answer. You could say r is negative 3, and these both represent the same thing. Does that make sense, right? So when I'm drawing out this cylinder, right, it doesn't matter if I'm looking forward, drawing it out ahead of me, or if I'm looking backwards or drawing behind me, like this. Maybe it's time to bring up my GeoGebra thing. Yeah. Look at this. I whipped up a uh, GeoGebra worksheet here that helps you maybe visualize cylindrical coordinates a little bit. So I can pick up this point and move it, right? And it'll give you at least the theta here, right? Although it uses an alpha, I hate that. This should be a theta, but I think it changed it to alpha on me. I'm not sure. But anyway, so if I was to just spin around, right, like this, it doesn't matter if I'm drawing ahead of me or behind me. Let me show you what that looks like, right? So if my point is here, let's say, and I turn off R positive and turn on R negative, do you notice I'm looking off to the left now? See that? Looking to the left, but walking backwards behind me to get me to the same spot. You see that? And so in that case here, we have, we're actually, that's a negative R case. Do you see that? So for visualization purposes there, this is actually kind of nice. I think, did I put this on the modules page? I may not have. Maybe, would anybody be interested in me uploading this so you could play around with GeoGebra a little bit with the cylindrical coordinates? Because GeoGebra does not do cylindrical coordinates natively. And so it might be nice to look at this and sort of just get a feeling for what this stuff looks like. Right? You can move this around like that. You can turn on the R positive, turn off the R negative, and then see if you can make sense of the coordinates. Now these are in radians, right? This middle one is in radians and not degrees. It's showing you degrees down here, right? But it's reporting your answer in radians, which is, by the way, required. Cylindrical coordinates need to be in, the theta has to be in radian measure. Absolutely, yes. Great. Yeah, I can do that. It's easy. I can upload this quickly. So yeah, that's no problem. Awesome. So let's get to what we were doing now, converting equations, converting rectangular equation to its representation in cylindrical, which is R equals 3. So that's an option. This is his second, just as correct answer. Either one of those is fine, right? Let's do another one real quick. Oh, and by the way, which one would you rather work with, right? I mean, think about if you had to solve this for y, which we often do, right? I would have to first subtract x squared from both sides, and then I would be taking the square root of 9 minus x squared. There's a couple issues with that. 9 minus x squared is, two terms, and the square root doesn't split over those two terms. And so I'm sort of stuck with this nasty square root. And you might remember from Calc 2, if I ever had to integrate over something like that, which we will do later in this course, all of a sudden we're integrating a nasty square root, which you might remember something called trig substitution as a method to have to handle those really ugly square root things, right? If at all possible, I would love to avoid integrating over square roots. Now, think about if you lived in a world, not rectangular, but in this world, you live here. Well, this surface, the same surface, is literally a constant in this world. This is literally just R equals 3. The height can be whatever it wants to be. The z value can be whatever it wants to be. And theta can be whatever angle it wants to be. And so that generates drawing out that cylinder in that way. So the only key information you need to generate this entire shape is just R equals 3. And you let z be free, and you let theta be free. And you can literally get to any point just knowing that R is 3. Do you see that? And so I would rather differentiate and integrate over this than square root garbage, right? So that's a little hint as to where we're going with this in the future of this class, yeah? Cool. Here's another one. Here's a paraboloid. It has the form, let's say, x squared plus y squared equals 4z. And if I want to convert this equation to cylindrical, well, I can again replace the x squared plus y squared with r squared, right? And that equals 4, and then I replace z. Well, wait, z is z. So I replace the z in rectangular world with the z in polar world, cylindrical world, and it's the same thing. So this is totally now a cylindrical equation. It's in terms of r's, thetas, and z's. Right? Now, again, you can simplify this. You can say that r is the square root of this, so you get 2 square root z. And you can even make a choice whether it's plus or minus that you want to take. But this would be one representation of that surface. Again, a little simpler. Right. Let's see here. Any others? Because all of these have the x squared plus y squared in them. Yeah, okay. This one does too. That's cute. Okay. Let me look at the homework real quick. See if there's just one more equation here that just doesn't quite work like the others. Let's see here. No, it looks like they often have that. So, all right, cool. All right, I'll just go through it then. How about this one? X squared plus y squared equals z squared. This is a cone. Well, this would end up being r squared equals z squared. And again, you can take the square root to get r equals z. You can get plus or minus z. Either one of those is fine. So you get here r is z. Okay. And here's a hyperboloid. X squared plus y squared minus z squared equals 1. Suppose you want to convert that to cylindrical. You just replace the x squared plus y squared with r squared. Minus z squared equals 1. And we usually solve for r. And so we'll end up having r squared equals 1 plus z squared. And here they don't take the square root, which is kind of interesting. Because if you did, here you would have to say that r is the plus or minus of the square root of 1 plus z squared, right? To make sure you're not, yeah. So you, again, I think you could capture either one of them. You could take the positive or the negative here. But they kept it with this. That's sometimes what they do as well. They sometimes solve for r or just r squared or something like that. Okay. All right, awesome. Now, just to show you that not all surfaces are amazing in cylindrical, what if I had this cylinder? Now, this is a cylinder. Y squared equals x, right? Now, that's a cylinder because it's missing z, right? It's missing the z, so it makes that a cylinder, right? It's a parabolic cylinder, if you will. And so cylindrical equations might be nice. Cylindrical coordinates might be nice here because it's a cylinder, right? Well, let's see what we can do, right? So first off, y's and x's are not allowed. And there is no x squared plus y squared to just replace. So here I have to actually go and replace the y and x with their formulas. Y, remember, is r sine theta. And x is r cosine theta. Okay. Squaring that out gets me r squared times sine squared theta equals r cosine theta. And I have a little bit of a tricky trig equation cooking up here. To handle this, I'm going to actually subtract this from both sides, get everything on one side, and then want to factor as best I can. I do want to avoid dividing, because dividing I might lose vital information, because I might make the assumption when I'm dividing that something is not 0 when it might be, right? So the safest way so you don't lose any information while you're doing this is to bring everything to one side and see if you can factor it instead, right? We'll have to deal with this some way with division soon, right? But maybe we'll get to work with this a little bit. Let's see what we got. Now, we can factor out an r, right? So this does become r times r sine squared theta minus cosine theta equals 0. And it looks like I have two options. Either r is 0 or r sine squared theta minus cosine theta is 0. Okay? All right, two options. This times this is 0, meaning one is 0 or the other is 0. This is a degenerate case, though, isn't it? R equaling 0. Think about that. That means that theta can look in any direction. Z can be any height, right? Any value. But R, you're not allowed to move forward or backwards. So do you see that this is really just the Z axis? R equaling 0 is every point on the Z axis. You see that? That's not what this is, right? This is sort of a collapsed version of this. This is not telling you the whole story. So I am going to ignore it. That is not what my shape looks like. It's true. If this equals this, then R can equal 0. That is true, right? But it's not the full story. So the full story, though, is here. Full story is here. This is the relationship that we're looking for. Now I'm going to solve for R here. So R times sine squared theta equals cosine theta. And now I have to be careful, but I'm going to divide now. So I am going to say R is cosine theta divided by sine squared theta. Said another way, this is lovely. This is cosine over sine, which is cotangent. And then 1 over sine is cosecant. Oh. Okay, so maybe I prefer y squared equals x, that version versus this version. But hey, I can at least think of it in the cylindrical world. So in the cylindrical world, the description looks like this. In the rectangular world, the same surface looks like this. And so now it's nice to pick and choose which one is easier. And so y squared equals x. Welcome back to Calc 2. That's right, exactly. Because now if I have to integrate that, you're like, oh boy, do I remember that? Now, I think this one's actually decently easy, but it's the other one, right? I mean, if this was like secant tangent, right? The derivative of secant is secant tangent, yeah? So that's actually not too bad to integrate. And this is the cousin of secant tangent. This is cosecant cotangent. So this is an easy one, but one that's probably not at the top of your head, right? So anyway, not all surfaces benefit from being represented in cylindrical. I guess that's the takeaway. Yeah, even some cylinders. So, but it's lovely when it does work, and it's lovely when it does simplify things greatly. All right. Cool. Let's see. What else can I say here? Ah, yes. So going the other way is a little is difficult. It can be not as straightforward. At least with rectangular to cylindrical, you literally at worst case are just plugging in what x equals, what y equals, and what z equals. Right? Going the other way, you have to hope that certain things show up so you can do the replacement correctly. Let me show you what I mean. So now, suppose I give you this in the cylindrical world. R squared cosine of 2 theta plus z squared plus 1 equals 0. Ooh, okay. So that is a cylindrical equation. It has r's, thetas, and z's in it. And I want to work with that, but I want x's, y's, and z's. Right? I want to convert this to rectangular. Convert to rectangular. Okay. The first thing I notice on this problem is the double angle. The double angle, right? And so cosine of 2 theta, I want to replace that most likely with an identity. Now, which identity? Because cosine of 2 theta is the one that has multiple possibilities for the identity, okay? There's one that involves just sine squared. There's one that involves just cosine squared. and there's one that involves both cosine squared and sine squared. I'll save you some time looking it up. This is the appropriate one in this case. Let's replace cosine of 2 theta with cosine squared theta minus sine squared theta. Now, why would I want to do that? Because I know good things happen when I have r and cosine together, right? Because r times cosine is x. R times sine is y. So thinking of this identity in this way makes something show up that I can use. So multiplying this through gets me r squared times cosine squared theta minus r squared sine squared theta plus z squared plus 1 equals 0. And indeed, r cosine theta, that's x. So this is going to be x squared. R sine theta is y, so this is y squared. Z is okay, right? Z is okay in rectangular and cylindrical, so leave it. Constants, of course, are okay. And so there we have it. We have that this is x squared minus y squared plus z squared plus 1 equals 0 in rectangular coordinates. And if you want to be super fancy, if you want to think about this, this is actually a hyperboloid of 2 sheets. Okay. Anyway, I converted it to rectangular. As you can see, this way, it's a little bit more of a puzzle. It's like, how do I get r cosine to show up, r sine to show up, so I can replace them with x and y? And that will usually involve some tricky trig into identity of some sort. And so there's no good step 1, step 2 process that you can work. These are sort of just puzzles that you have to work on and just figure out the right combination. Okay. All right. You ready to switch coordinate systems? Let's introduce another one. We've been talking about cylindrical. Let's now talk about spherical and see how spherical coordinates will work. Of course, as the name suggests, spherical coordinates are going to be super handy when working on a sphere, for instance, right? And so let's go ahead and draw a picture on how this is going to look like. So spherical coordinates. Coordinates. Yeah, I think I spelled that right. It didn't look right for me. Okay. X, Y, Z. All right, let's put point P down. I'm going to drop its shadow again. This time, I'll just put it in the first quadrant, right, like that. Okay, so we have that. And here are what the coordinates look like. We're going to have a rho. That's not a P. That's a Greek letter rho. R-H-O, rho. The second coordinate is theta. The third coordinate is phi. We got some Greek letters coming up, and when we use Greek letters, we usually mean angle, right? So theta is an angle. Phi is an angle. Remember how I was talking about hybrid before, where cylindrical was a hybrid between polar, which had one angle and one directed distance, and then rectangular, z, right? This has 2 angles and only one directed distance, right? Only one. And in fact, this is not a directed distance. Directed means could be positive or negative. This is just plain old distance. In this coordinate system, we disallow rho to be negative. Rho must be 0 or positive in this because rho represents the distance, straight up distance from the origin straight to the point. This is rho. That distance. Now, to give me perspective here, here's the shadow of that line segment that I just drew. See that? That's the shadow there. Okay. And so Rho is the distance from the origin to the point. Where's theta? Theta is the theta from polar. So theta, again, is this horizontal rotation right here. So that's the same theta. So I'm going to look at the shadow, the projection of this segment onto the xy plane, and then measure the angle between the x-axis, positive x-axis, and that shadow line. That is theta. Then a third angle is the angle between the positive z-axis and this line segment. That is what phi is. Okay, so to get to this point, think of this as a couple of motions, right? What you're going to do is you sort of start looking out this way at the positive x-axis, right? Maybe pointing straight up like this. You rotate theta, then you rotate phi, and then you go straight, right? So it's sort of like you go around, you're like this, you do your theta rotation, then you do your phi rotation, and then you go straight, like that. Yeah, so those are the three things there, okay? That's the relationship there. Now, be careful reading other books. This is not, I feel this is pretty standard, and more books are doing this, but there are some older physics books, there are some older math books that like to swap phi and theta, and they literally mean the opposite. They literally mean the opposite. So if you grab a random book and you're looking at spherical coordinates, you have to make sure that their theta is our theta and that their phi is our phi, because it could be well enough that they've just swapped them, right? Now, I think more modern books have sort of settled on this, and the idea being that they like theta being the same theta from polar, right? And so some books, though, will call that phi, and some books will call this theta, yeah? I was reading an orbital mechanics book the other day, and they have it swapped. And I've been teaching it this way for so long, every time I saw it, I'm like, wait a minute. And so you want to make sure when you're looking at other resources that you're very clear on how they describe spherical coordinates, okay? All right, let's get to the business of converting. How do I get back to x, y, and z from this? Well, draw this picture, right? So again, the x, y, z coordinate of this point is going to be some x distance, right? Like here. Some y distance, like that. And then some z distance, right? Okay. By the way, this length of the shadow, that projection, we have a name for that. That's something we did in polar. That is r. Now, I bring that up because I want to figure out what is, let's try, let's see, which way do I want to do this? Yeah, I want to get a hold of what x is right there, okay? Well, the first thing that I look at here that I notice is x is a leg in a right triangle. In fact, it's this right triangle laying down on the floor. Do you see that? There's this right triangle laying down on the floor. X is a leg, Y is a leg, and R is the hypotenuse. Right? And in fact, that's exactly how we got the statement before that X is our cosine theta. Right? Because cosine of this angle is the adjacent side. The adjacent side is X, and divided by the hypotenuse, which is R. So cosine of theta is X divided by R. This would be good because theta is allowed in spherical, but R is not. R is not a member of spherical coordinates. So what that means is now I need to find a description for R in terms of spherical coordinates, in terms of rho, theta, phi. Okay. Well, I notice that R is a leg of a right triangle. This right triangle is standing straight up. See that? And I would really love to relate it back to phi. But the slight issue that I have here is phi is not inside of the right triangle. Would you agree with that? Phi is over here. I would really love phi to be here. But wait a minute. This is parallel to this. So phi also lives here. Right? Now, phi by definition is here. But by geometry, would you agree that whatever this angle is, it's also this angle because parallel lines being cut by a transversal? Oof. When's the last time you heard that? Literally geometry class, probably in a high school geometry class, right? So we have literal parallel lines being cut by a transversal. So alternate interior angles are congruent. Did I just say that? Did I just come up with that? That is like triggering a memory of geometry a million years ago.
Not a good one.
Not a good one? Oh, sorry. Well, in good news, it is a good one for our purpose because do you notice that R is opposite now? Is the opposite side of phi? Phi lives up here. R is the opposite. That means that R has something to do with the sine of phi. So what is the sine of phi here? The sine of phi is going to be its opposite side, which is R, divided by the hypotenuse. And look at this. The hypotenuse of that triangle is rho, which means that R is rho sine phi. Good news. This means that X being R cosine theta, what is R? R is rho sine phi times the cosine of theta. That's how I want you to remember this formula. X is this piece, which is the R, rho sine phi. So this is X is R cosine theta. You already know that from polar and cylindrical. Just replace the R with what it's equal to, which is rho sine phi. Especially because look what I'm going to do next for Y. Y is R sine theta. But wait, R is R, right? So this is going to be rho sine phi again, because R is R sine theta. So that's how you memorize these conversion formulas, X and Y. You know X is R cosine theta and Y is R sine theta. All you have to now remember is R is rho sine phi. So it's the same term in both of those, like that. Okay. What would Z equal? Well, back to our picture. Z lives right here. Z is the adjacent side relative to phi. So this is actually going to be pretty straightforward. That has to involve the cosine of phi. And so we will know that the cosine of phi is going to be the adjacent side, which is Z, divided by the hypotenuse, which is rho. So I get that Z is simply rho cosine phi. All right, they're not as pretty as cylindrical, but there we have it. We have our conversions. You give me a spherical coordinate, I can plug in the rho, the phi, the theta, and I'll get you the XYZ. Okay. Love for you to take a moment to study that picture. And I would love for you to be able to, I'm not going to test you on this, but it would be amazing if you could like regenerate these formulas from your understanding of drawing a picture. That would really show yourself that you know and understand the geometry that's happening, right? And in fact, you know, I don't necessarily tend to memorize this, although I have, because I've used it quite a bit now. But I could totally regenerate this at any time because I understand the pieces and the drawing behind it. Does that make sense? And so that's a much more confident way to have knowledge. Yeah. Instead of relying on memorization, which can be shaken, especially when anxious, right? During an exam or something like that, right? Or during a high stress situation. Memorization tends to fly out the window, right? So if you can fall back on a more reliable way of recalling things, that can be super helpful. Now, I'm not saying, you know, don't memorize anything. I'm not going that far either, because memorization's good, it's quick, and when it works, it's fast, right? If I had to redevelop everything from first principles, well, it would take me all day to do literally anything, right? So there is a give and take there, but this is a nice way to remember and connect those ideas here. with working with that. Okay, let's go the other way. Can I relate rho, phi, and theta to x, y, and z? Okay. Well, one way that we can do this, right, is notice that rho is the hypotenuse of this standing up triangle, right? And so we would know that rho squared has to equal r squared plus z squared by the Pythagorean theorem. But wait a minute, r is the hypotenuse of its own right triangle involving x and y. So guess what r squared equals? Oh, well, Polar told us as well. R squared equals x squared plus y squared. So that tells me that rho squared is actually x squared plus y squared plus z squared. So you tell me the x, y, and z coordinate, and I will tell you that rho has to obey this equation. Okay. Now, it looks like rho could be positive or negative, and mathematically that's true. If I solve this, there's going to be two options for rho, a positive or negative number. However, by definition, we don't allow rho to be negative. So that takes a lot of the mental worrying about that sort of quadrant thing that we had going on, at least for rho. We know that rho has to be positive. That's by definition. We take rho to be positive. Okay. Awesome. Now, theta is the theta in polar. So it's our old friend. Tangent of theta is y divided by x. That's the same relationship that held in cylindrical, and it holds in spherical because it's the same theta in both worlds. So nothing new there. Right? Now, I will write this formula in a little cheating way. Okay? This gives me what phi is. Well, actually, it gives me cosine of phi. Would you agree the easy way to say this would be that cosine of phi is z divided by rho, right? Just by solving this for cosine of z. Now, it's cosine of phi. Now, someone might balk at that. They might be like, wait a minute, there's only supposed to be x's, y's, and z's on the right-hand side, right? And you've cheated here. This is z divided by rho. Okay, that's fine. What is rho equal to? You could write this formula as z over, solve that for rho, the square root of x squared plus y squared plus z squared. And while being true and also just having x, y's, and z's in it, it's so much uglier to write it that way. So I always just think of it like this, right? And that basically just gives me, this formula to memorize. That it's either z equals rho cosine phi, or cosine phi is just z over rho, right? So it's the same thing doing double duty here. All right, but there we have it. Those are our conversion formulas. This is spherical to rectangular, and these are rectangular to spherical. Okay, let's do a couple examples. Okay. Let me see. I don't see any example. Hold on. Let me go to the homework here. By the way, I'm only interested in relating back to rectangular. So I'm not going to give you any problem that says convert spherical to cylindrical. All of our problems are going to go through rectangular. Does that make sense? Right. So be able to do spherical to rectangular, rectangular to spherical, cylindrical to rectangular, and rectangular to cylindrical. But you don't have to go from spherical to cylindrical. In the real world, we just go through rectangular anyway. So we don't go directly, unless you're doing like a million problems in the real world. Usually that's good enough just to do that. Okay, let's do a couple problems here. I'm going to give you a rectangular coordinate. So this is -5, -5. comma, square root of 2. This is rectangular. And I'd like you to convert that to spherical. Okay. So we're given an x, y, and a z. And I want to come up with rho, theta, and phi. Okay. Rho squared is going to be x squared plus y squared plus square root of 2 squared. Okay. That's going to be 25 plus 25 plus 2. So I get 52, which means rho is this lovely number, square root of 52, which I don't think is a nice square root, right? It's a little bit over 7. But nonetheless, that is what rho is. And notice not positive, negative. It's just positive. We take rho to be positive. Okay. Now, again, you might want to look because we are going to have the same, because theta is the same problem. And so we are going to have some coordinate issues. We're going to have some quadrant issues. So I definitely want to graph this just at least to see where I'm at roughly. Okay. So x being negative puts me over here. Y being negative puts me over here behind and then up there. So I'm over here somewhere. Right? So theta might be a third quadrant angle. Right? Or, right? Oh, I don't have an or because I have to be walking forward because spherical. So I definitely need theta to be a third quadrant angle. Theta is third quadrant. See why you need to draw a picture for these? You need to know what quadrant theta is in. Okay, let's do it. Tangent of theta is y divided by x. Y is negative 5, x is negative 5. This tells me that tangent of theta is positive 1. Tangent is positive in the first quadrant and the third quadrant. I need the third quadrant angle, right? So when I go to my calculator to find the inverse tangent of 1, which you should, that one you should probably know, is pi over 4, 45 degrees, right? My theta better not be pi over 4, because pi over 4 is looking this way, and that's looking in the wrong direction. Yeah? I better take the third quadrant angle. So I can use my calculator to get the reference angle of pi over 4, and then adjust accordingly. This should be pi plus pi over 4, so that's 5 pi over 4. So that tells me that theta has to be 5 pi over 4. And technically any 2 pi k multiple thereof. Right? But we keep within 0 to 2 pi. Okay? So that's my theta. Let's now do phi. Phi, well, I can't do phi directly yet, but what I can say is that the cosine of phi is z divided by rho. Z was given, root 2. Right? Rho was calculated, root 52. Okay. And I don't think this is pretty. Yeah, this is not going to work. This is, what would this be? This is the square root of 2/52. Are you kidding me? The square root of 1 over, what is that, 26? Yeah, that's not going to be a pretty number. So this is good. This is instructional. Because what I can do now is show you how I would handle this. What's beautiful about phi, okay, is that phi is, if you notice, phi looking straight up is 0 radians, and I can only rotate 180 degrees, right? Because if I think about it like this, right, with phi, right, if I was to rotate this down like this, there's 90 degrees for phi. Here's 180 degrees. It's now a straight line. If I go past that, like this, do you notice that all I've done now is make an angle here, right? And so I would just have to turn theta around to compensate. Bottom line, phi is only measured between 0 to pi radians. In other words, it's only from 0 to 180 degrees. This makes the inverse cosine completely safe. Whatever the calculator says here is the angle you want to go with. So unlike theta being a jerk and being like two options for quadrants, phi is straightforward because of the way we define phi. Phi is either first quadrant or second quadrant, and the calculator will always tell you the correct quadrant, right? So this one directly is just the arc cosine of this number. So typing that in, make sure you're in radian mode, because you must report your coordinates in radian modes, real numbers. So I'm going to do inverse cosine of square root of 1 over 26. And so I get that phi is about 1.3734 radians. And that's the best I can do. So let's put this all together. My spherical coordinate is going to be square root of 52, comma, theta, which is 5 pi over 4, comma, phi, which is 1.3734, and so on. Those are my spherical coordinates. Okay. Now, in the future, what we're going to use this for is the following calculation. Okay, and I want to finish this up. I know this video is getting kind of long already, but I don't want to leave it for the next video, because I think this calculation is going to have some stuff to it, right? So let's see what we got. We'll finish it. This will be the last thing we do, though. Okay? Let's convert a cone to spherical. Okay, so the cone we have is given to me as x squared plus y squared equals z squared. Okay, and I want to convert to spherical. Okay, now spherical has as a rule x squared plus y squared plus z squared. But do you see, this is not what I have. I have x squared plus y squared, which starts out great, but then it's minus z squared if I bring that over. So that's not quite good enough to just say it's rho squared. Well, not seeing any immediate tricks, we just dive right in and replace x, y, and z with their formulas in spherical. This problem is going to get a bit ugly before it gets cleaner, but it will get pretty clean. I promise that. So here we go. X is rho sine phi cosine theta. So that's going to be all that squared. Plus y is rho sine phi sine theta squared. And that has to equal z, which is rho cosine phi, and that's squared. Remember what I said about ugly? It's going to get ugly. Okay. Now this isn't too bad because this times this, so there's no like foiling or anything. So this just is rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. And that equals rho squared cosine squared phi. Okay. I see some good news. Look at this. There's a common factor. We have rho squared sine squared, rho squared sine squared. See that common factor? I'm going to factor that out in front. Leaving cosine squared theta plus sine squared theta. Ooh, did you see what just happened? Cosine squared theta plus sine squared theta is 1. All right, identity. That's cool. So this just gets replaced with a 1, so this is this times 1. Oh, that's nice. So that gets me rho squared sine squared phi equals rho squared cosine squared phi. Okay. All right. Now, your book does do division here, and it's okay. You're not going to lose anything by division. I would still subtract this from both sides, factor out the common rho squared, and then cancel it, right? But knowing that I'm not going to miss anything if I do that, look what happens here. I get sine squared phi equals cosine squared phi, right? Dividing both sides by rho squared. That's assuming that rho is not the constant 0. Okay? And if rho was the constant 0, this is literally just the point at the origin. If you're not allowed to go directed distance anywhere in any direction, you're 0, you're stuck at the origin. That's not what this cone looks like. So I know that that's not happening. Okay, now, what the heck do I do here? Well, is there a way that I can get information about phi? Because it looks like everything else sort of canceled out. Theta left, rho left, and it looks like I only have a requirement on phi. So one thing you could do is we can divide by cosine squared, both sides. Cosine squared divided by cosine squared is 1. Sine divided by cosine is tangent. So this is tangent squared phi equals 1. And now I can take the square root of both sides to get tan phi equals plus or minus 1. Right? Plus or minus the square root of the other side. But wait a minute, those are nice. Tangent being positive 1, right, means that either phi is 45 degrees, pi over 4, or if the tangent of phi is negative 1, 3 pi over 4. Okay? So it looks like a cone with this shape can really drop down to just being a constant in the spherical world. Let's imagine what we can do with that. What does that look like, right? So remember that phi is an angle measurement from the positive z-axis. What happens if phi is pi over 4? Well, that means I'm making a 45-degree angle, right? 45-degree angle with the top, with the z-axis, right? Now, theta can be any angle it wants to be. Yeah? Right? And rho can go any distance that you want. So notice that that does indeed make a cone. You see that? It looks like a sort of a triangle on this view, right? And I have my cone, just like that. And so, yeah, a cone can be represented by just literally the angle phi. Pi over 4 gets you the upper part of the cone, like this. And 3 pi over 4 gets you the bottom. I can't do this with my, I can't go all the way like that. I'm not that ambidextrous. But anyway, now this is below. And so now that would look like this, right? 3 pi over 4 this way. Right, here's 90 degrees, pi over 2. Then there's 3 pi over 4. And so then that would be the bottom part of the cone. Do you see that? And so, if I had an option, I would rather work with this, phi equaling a constant versus this sum of squares thing, business, right? And in fact, there's going to be a problem in the future where we actually take this cone and do some calculus on it, and we will definitely want it to look like that. And that's going to simplify our life with that, yeah? All right, everyone, that finishes off what we got going on for today. And that finishes off chapter 11. And that finishes off, of course, 11.7. And so practice, practice, practice. Again, I would really suggest that you work through the review exercises of chapter 11 in preparation for your exam. But the exam won't open up until Monday next week. All right. So take this week to prep. Keep keep sort of going at. I'm on Thursday. I'm going to go into the next chapter, right? So I understand maybe if you'd want to hold off and not watch the next video right away until you're really prepared for chapter 11, but don't let chapter 12 sneak up on you either. And I would love to see you, people who are live today on the Zoom meeting. I'd love to see you again on Thursday, even though it's going to be new information. I hope you would still try it and come out to talk about the new stuff, right? Anyway, with that being said, I hope everyone's doing well. I can't wait to check in with you guys on Thursday. And until then, be well, and I'll see you next time. See you.
Bye.